get started. Today it's a pleasure to have Paul Romatschke visiting from University of Colorado, Boulder. So Paul's an expert on a number of different things relating to relativistic heavy ion collisions, relativistic fluid dynamics, gravity, ABS CFT as applied to these systems. So today he's going to tell us about a bit of a broad topic relating to this general class of things. So go ahead and take note.
Thank you very much. Let's see if this works. Yeah, so I'll talk about the absence of local rest frame in far from equilibrium quantum matter, and I will define or try to define these concepts here during the talk. So this is mostly based on a work that I did together with my collaborators Peter Arnold and Wilke van der Schie, that's summarized in this paper here. And since I didn't know the audience very well, given that I have not been giving talks here before, some of the things may or not be known to you. If you want me to go into more detail about something that's on my slide, just stop me and ask me a question. I'll be happy to sort of spend more time on sort of whatever part of the talk you find more interesting. So the motivation basically starts with the essentially problem of equilibration in heavy ion collisions, and I'll talk about that in the first part of my talk. Then I'll talk a little bit more about the actual topic of my talk, the absence of a local rest frame. And in doing so, I'll tell you a little bit about why and how this sort of relates to numerical GR. And if I get to it, I'll talk about black hole collisions that we sort of study numerically and what that has to do with it. OK. So as I sort of said, the motivation for at least us originally came from these experiments here conducted at the Relativistic Heavy Ion Collider and the Large Hadron Collider. And they involve basically the acceleration and collision of ions to macroscopic energies. So typically at LHC, a single ion is accelerated to kinetic energies of about 300 TeV. And that basically is the kinetic energy of a housefly flying with about 3 meters per second, just to give you an idea of how energetic these individual ions are. So the idea with these experiments is to study a form of matter known as the quark-gluon plasma. And just a sort of basic physics introduction to that, the idea is that you sort of heat up the atoms enough to strip the electrons. Then you basically create ordinary plasmas. That's what our colleagues trying to build up fusion reactors do. That's not the plasma that I'm talking about. So basically, I talk about what happens if it dissolves protons and neutrons to a state of matter that's called a quark-gluon plasma. And the analogy is such that instead of studying photons, so the U1 interaction, we study gluons, which has an SU3 interaction. And the difference there is that SU3 is a non-abelian gauge theory. And as such, basically, even sort of the gauge theory itself has non-trivial interactions. In particular, sort of you can have gluon-gluon scattering, direct gluon-gluon scattering, which you do not get by just looking at the photon-photon scattering. You need electrons in electromagnetism to make the same process happen. And that sort of is of importance to the dynamics. And in particular, sort of for what I'm concerned, I'm interested in these non-abelian gauge theories, not necessarily only the theory of strong interaction QCD, but more broadly classes of non-abelian gauge theories. And they have to be non-abelian because otherwise I lose sort of these particular issues. OK, so I wanted to sort of give you a sort of basic physics reminder of how extreme sort of these quark-gluon plasmas are in terms of other environments. I will argue that in some sense, quark-gluon plasma physics or heavy ion collisions is essentially an extreme form of condensed matter physics. The idea being that most people would sort of consider the flame and the Bunsen burner to be an extreme environment, but that's only about 2,000 Kelvin, so it's a sort of fairly small temperature if you think, for instance, of the sun, which has a core temperature that's about 10 million degrees. But we are not done with extreme environments. We can sort of think about our fusion friends here. This is a snapshot of the ITER detector, ITER reactor, I'm sorry, in Cadarache. And the idea is that you sort of create conditions that essentially form fusion environments, such as the center of the star. But given that you don't have the gravitational pressure in the center of a star, you need to sort of compensate somehow to get the reaction rates up to the same process. And the way you compensate is that you heat up the system much more. So for fusion, you would need temperatures of about 100 million degrees. And the main reason is that you don't have the gravitational confinement that you get in stars to get fusion going. So in terms of extreme environments, supernovas are pretty much as extreme as it gets in our universe. Those reach temperatures of about 10 to 11 Kelvin, as sort of many of you probably know. But I'll argue that in the case of heavy ion collision, we probe temperatures that are even higher than that by an order of magnitude. We probe temperatures regime that are on the trillion Kelvin range, 4 trillion Kelvin to be exact. And that's sort of a snapshot of what you see in the detector. So these are all individual particle tracks. There's a beamline that's sort of coming in here. So you have the collision in the center of this object. And those are the charged particle tracks that you see in one of these collisions. And from that, you can infer the temperature of the system that you created. And that's sort of the number that you typically sort of get from this. So in that sense, really sort of we sort of study certainly very extreme temperatures. And that's what I sort of, that's basically the reason that I sort of say that this is a form of extreme matter condensed matter physics. Again, the characteristic numbers of these quark gluon plasmas, I talked about the temperature. If you think about the physics of these systems, it's such that you create this very small, very hot system. So remember, these are the size of ions. And then, because there's nothing to sort of keep the system together, the system will expand and cool. And if you sort of do the math, you find that the typical lifetime of these systems is very short. It's about the length of a nucleon, 1 femtometer, a Fermi, over the speed of light, because the systems expand at the speed of light. So typically, you find lifetimes that are on the order of 10 to the minus 23 seconds. And the size, again, is sort of given by essentially the size of an ion, the radius of gold, for instance. That would be about 10 to the minus 14 meters. So these are the characteristic sizes and lifetimes and temperatures. I will argue that I can try to model this system using fluid dynamics. And I will sort of come back to why I think I can do that. Let me tell you a little bit about the theory of relativistic fluid dynamics. First of all, why does it have to be relativistic? Well, here in this heavy ion collision business, we don't deal with curvature of space-time, but we deal with velocities, fluid velocities that are approaching the speed of light. So we need relativistic fluid dynamics in that sense. So it's relativistic in the sense of special relativity sense. There are some relations to gravity, though. If you sort of want to set up a theory of fluid dynamics from first principles, you think about it as an effective field theory. You sort of have to define what are the effective degrees of freedom. For a fluid, that's not hard to do. Fluids have fluid velocities. Think of other things. They have pressure. Like if you look for an atmospheric science forecast for tomorrow's weather, you sort of have highs and lows. That's the pressure. The pressure and or energy density. In this case, has to be energy density, not density, for reasons that I'll come to in a moment. So the pressure and the energy densities are synonymous because they have to be related by what's known the equation of state. So that's something that you sort of need to provide. So that's two of the degrees of freedom that we have identified. And then since, well, if you think about it really from a GR perspective, the metric of space-time is also a dynamic variable in the sense that it can change and it will introduce gradients. So you add it to the possible degrees of freedom. So I argue that if you want to write down a theory of relativistic fluid dynamics, the energy density, the fluid flow velocity, and the metric of space-times are sort of good degrees of freedom. And then obviously you can sort of say, okay, let me now add gradients of these fields and second gradients of this field in an effective field theory expansion. What is the fundamental object that you have to sort of write down? Well, if you look at any textbook on fluid dynamics, you'll find that fluid dynamics is nothing else but the conservation of energy and momentum. So a good object in a relativistic setting would be the energy momentum tensor, T mu nu. You also have to specify what the symmetries of the problem are. So in my case, since I will sort of talk about isotropically expanding fluids, I sort of say that the whole Poincare group is a good symmetry group for my case. If I were to study fluid dynamics of a crystal with a preferred direction, that group would be broken, and I would have to use a different symmetry group, and it would get different fluid dynamics equation, just as a side note. But for me, basically, I sort of can, since I have no constraints, I can use the full Poincare group as a symmetry group. Then, basically, I'll argue that you write down the most general object, the most general expression for T mu nu from these basic building blocks. And if you, as a first step, don't allow any gradients of the fields, just the energy density, the fluid velocity, and the metric, there's essentially a unique expression that's dictated by the Poincare group that you can write down. And you can find that expression either by sort of doing what I just said or looking it up in Lambda-Lifshitz. And then if you sort of look at the conservation equation for the energy momentum tensor, d mu, T mu nu, and you can actually sort of promote this to a covariant derivative, then you find the familiar Euler equations. It's nothing more than that. So some people think this is sort of magic, that the Euler equations come out from basically this recipe here. Other people sort of say it's trivial. I don't know. The answer is probably somewhere in between. But that's really sort of the way that, at least in my community, people think about fluid dynamics. It's an effective field theory in gradients of these basic quantities. And if you don't allow any gradients, then you get the ideal fluid dynamics or Euler equations out of this. We can correct things, improving our theory by sort of going to the next order, meaning allowing first order ingredients. If you do that, if you allow first order ingredients, then those same equations, well, not very surprisingly, turn out to be the familiar equations of Navier and Stokes. So basically, if you want to, I can derive all of atmospheric science from first principles without ever sort of having to think about what sort of system I actually model. And that's sort of the beauty of fluid dynamics. None of the recipes that I sort of have given you here depend on the actual system. Fluid dynamics is a universal theory of anything which has small gradients. What that means is that you take any matter, no matter what it is, you sort of wait an extremely long time, you look at systems that don't have any sharp edges or gradients, then my claim is that all of those, provided that the symmetry group is correct, will behave according to fluid dynamics. That's a question.
I would have thought that an element on this list was local thermal equilibrium.
Right.
In that derivation. Is that a fair statement?
So in some sense, that's implicit in the sense that I've said that I want to have an equation of state. Yes.
I thought that the derivations actually do. I mean, there's a elimination.
No, they don't. And no step is an explicit mention of thermal equilibrium.
Okay.
Yes. And you may wonder about that. And actually, sort of people have written papers about thermal equilibrium not being a necessary ingredient into fluid dynamics. There are people sort of push the idea that if you have, for instance, a non-thermal state, like a quasi-stationary fixed point, then the behavior of the system around that fixed point might be governed by fluid dynamics equations. I don't think there's a proof for that, but it's true that nowhere in this list does thermal equilibrium actually enter.
Okay.
Yeah.
I thought there were you might have gotten extra terms that you can eliminate by thermodynamics.
Not really. So the one ingredient definitely is the equation of state, and that at least sort of somewhat relates to thermal equilibrium. I mean, there must be a relation between pressure and energy density. That's sort of a unique and not time-dependent sort of expression. But other than that, equilibrium doesn't figure in this expression. It's true that sort of the usual notions sort of employ that, but in this case, no. Okay, so I told you about the first order theory, and you get the familiar equations of Navier and Stokes. And in principle, if I was actually doing that atmospheric science, I could stop here and be happy in solving my equations and get everything that I wanted. For relativistic systems, however, there's a problem. the relativistic Navier-Stokes equations don't obey causality, which might come as a surprise since I said that I want to have the Poincare group as my full symmetry group. But it just turns out that the way that the equations sort of promote or sort of propagate disturbances is that if I sort of disturb my system over here, the system immediately knows about that perturbation anywhere else in spacetime. That's the way that sort of Navier-Stokes essentially encodes diffusion, for instance. So diffusion equation is actually a good example because diffusion equation has the same problem. It's first order in time, but second order in space. And that breaks causality. It's not a propagating mode, but it's a diffusing mode. But nevertheless, it means that you violated causality. And what that means is that if you were, in a relativistic context, try to solve these equations, and you had broken causality, then something bad would happen. Typically what happens is that there are instabilities that correspond to these modes that sort of, you didn't treat properly. So in a different context, actually this was known to Maxwell already. That's the Maxwell of the Maxwell equations. And back in the day, he and other people came up with a solution for that, namely to say that, okay, if you take the diffusion equation, which is first order in time and second order in space, that's bad, but we can repair it if we sort of somehow manage to rewrite it in such a way that it's second order in space and second order in time. And explicitly, the way that this works is to say that, okay, if we want to have second order time gradients, we basically need to be one order higher in the gradients of our approximation. So really, we sort of should look at second order effective theory here, and then sort of do some resummation scheme. In the modern context, this is sort of sometimes known as causal relativistic fluid dynamics, Isler-Stewart theory, second order viscous fluid dynamics, and so on and so on. There are different names. All of them have the same character. You sort of include second order gradients in this whole business, and then you do an effective resummation of parts of those higher order gradients to get structures that are causal, basically. So what has happened in sort of the high energy nuclear physics community, for instance, is that people have sort of worked on these equations, were able to sort of find all the terms that are allowed to second order, resum them, and sort of make this whole thing into a workable theory that you can put on a computer, solve, and there are no ambiguities, basically. This is an example of what you can do with this. There's one particular observable, which I'll talk in a moment, that comes out from these second order viscous fluid dynamics equations. And it's sort of plotted as a function of centrality percentile, where this is just a code name for the impact parameter of these nucleus-nucleus collisions. So 0% means that the collision of these two heavy ions, in this case, was fully central. And 100% here would mean that they missed each other. They didn't actually collide. Okay? And there is experimental data for these different centrality classes that's sort of given here, and that's data from the Alice experiment that was taken at the LHC. And these different V's here are what's called momentum anisotropies. If you're expert in the field, you might know this as elliptic flow, triangular flow, quadrupole flow, and so on. And for people here, they might sort of be more used to sort of, basically what these in some sense correspond to are different L modes in the CMB spectrum. That's basically what they are. This is something like L2, L3, L4, L5. And you already sort of see the difference here in these sort of heavy ion collisions. The experimental accuracy peters out at around V5. You can't really measure V6 with a non-trivial error bar anymore, simply because of statistics already. However, again, as a difference to cosmology, you can sort of calculate or actually measure these properties as a function of the impact parameter of the collision energy. So you have many more handles on the experiment rather than have to deal with one universe where you sort of measure all of these things. But they are sort of similar. The important part of this plot here is these lines here, the different colored lines here with the bands here, come out from the fluid dynamics, solving the fluid dynamics equations that correspond to the initial setup for this particular experiment here. And as you can sort of see, there is a very good agreement between this theory and the data. So that's just one example. If you sort of look at other things, you basically find that the hydrodynamic models pretty much correctly describe 99% of the particles that come out from these experiments. So a very, very good description of the data, assuming that you can actually use these fluid dynamics equations. And in some sense, at least in the early days, 2003, when the first collider turned on, it came as a surprise to many people that this fluid dynamics description actually worked out so well. Because people thought that, okay, in QCD, you have a property that's known as asymptotic freedom, meaning that if you go to very high energies, the coupling gets small. If the coupling is small, the interaction between the particles should be almost like that of a free gas. A free gas, an ideal gas, is the complete opposite of an ideal fluid. Ideal gas means almost no interaction, very bad transfer between space anisotropies to time to momentum anisotropies. Basically, if I go back to the figure here, if you assumed an ideal gas, all the theory curves would be essentially corresponding to 0. You wouldn't get any one of these momentum flow coefficients. And if I may, sir, the main reason is that if you think about a collision where you have two of these heavy ions colliding and sort of forming an overlap region that sort of has some anisotropy, typically being almond shaped. So these are my two nuclei. They collided and they produced an overlap region that looks like this. Then the main point is that, okay, the distance between the center and this point here is shorter than the distance along that direction. The pressure in the center is one value, and you have basically a vacuum outside all over here. And that means that the pressure difference between, in this direction, basically, is larger than the pressure difference in the other direction. So from fluid dynamics, you find that the velocities are proportional to the pressure gradients. So you expect the system to flow faster in the direction that has a larger pressure gradient than the other one. And this is essentially what is found in this figure here. Whereas if you think about an ideal gas, then an ideal gas doesn't sort of know about those correlations. It just expands isotropically. So in an ideal gas, that doesn't matter. You basically get the system to be expanding isotropically for all of time, and you wouldn't get any one of these correlation coefficients. So that basically, in a nutshell, is what it would look like if you had an ideal gas, all these theory curves would be consistent with 0, basically. So essentially, the upshot of this is that maybe, surprisingly, the data tells us that the extra systems created in these heavy ion collisions behave very much fluid-like. So that's, in some sense, an experimental fact. If you think back about my motivation slide here, where I talked about these key characteristics of these plasmas, if you look at these values and sort of think about, well, the system only lives 10 to the minus 23 seconds, then if you think about just the absolute magnitude of these gradients, you find that these are extremely large. This system is exploding. It has large gradients. It's very short-lived. It's very small. So you would think that if this system does anything, then it certainly would not be hydrodynamics. It would more like be a gas. That's a question.
So I just wanted to understand a little bit more what's involved in the difference between the fluid and the gas. Fluid meaning less compressible or more viscous, or?
So, I mean, fluid in some sense, I mean, if you think about the extreme case, an ideal fluid would be a fluid that doesn't have any viscosity. It would be an ideal fluid. Okay. That's the complete opposite of an ideal gas, which in some sense has infinite viscosity. Doesn't have any momentum transfer whatsoever. If you think about the viscosity of any system that has some interaction parameter.
When we think about gases,
Yeah.
Some context, I guess, they effectively have.
Yes, gases can be fluids on some time scale and some length scale. But on the same sort of length scale and time scale, there's a difference in the sense that how strongly do these systems interact. And the characteristic parameter, for instance, shear viscosity over entropy density, for any system that has a coupling parameter, basically goes like 1 over coupling squared. So if the coupling is small, you're in the almost ideal gas limit, this viscosity coefficient would be large and would be a bad fluid. Okay? More questions? Okay, yeah.
Well, just the general context. So, given the nature of a collision, a natural way to do it would be to use the hierarchy of distribution functions, and that would be the sort of more fundamental thing to begin with, from which the hydrodynamics would arise. Now, one of the great things about that is that, first of all, you can deal with a multi-component system. Here, you're saying that it's all in the quark gluon plasma phase, but as it propagates, a number of things happen. It essentially, you get a breakout because it's doing the speed of light, and you get hadronization and all of that stuff. And that would be a breakdown of the simple hydro description because you have essentially the velocity distribution probability is not the kind of thing where you can close off the hierarchy. So what you're interested in is a region in which you've essentially said, this shall be the region that hydrodynamics works. And then there is a transport part of it, which is not, in which this is still applicable because you're always transporting momentum. It's just that you start to get different kinds of species forming, which can basically move relative to each other. And that would be, I would think, a more complete description of the system if one was modeling the full thing. And I think that what to focus on here is that very internal situation where you have a lot of back and forth in the degrees of freedom. So that number one, you're treating it as a bunch of stuff that has a single sort of pressure model. But that won't be true as the region is increasing its volume. It will start to go into the hadronization regime. So at what point in terms of these things, I mean, I guess that data that you're looking at is interpreting the results in terms of exactly that hadronization, the gluonic phase, and then somehow there's been a selection.
No, it's not. No, so what is actually done, and I didn't talk about this, is actually you only use the fluid dynamics for the quark gluon plasma phase. Then there's a freeze-out mechanism in which you sort of transfer the degrees of freedom to actual hadrons, and these spectra here are actually corresponding to the hadron species that are actually being measured.
Okay,
yes,
so
I didn't tell. Yes, yeah. So they're actually apples-to-apples comparisons. It's not a simple model where you just compare gluonic degrees of freedom.
So in other words, the actual model that people are using is a hybridization. So it isn't like, that full Landau model of collisions. It's actually a much more direct model.
Yes. And the other thing I wanted to say is that, yes, there is a way where you can derive fluid dynamics from kinetic theory using, for instance, BBKGY hierarchy truncation. The problem is that assumes that you have well-defined quasi-particle states.
Yeah, that's true.
We have a lot of indication that suggests that there are fluids out there that are very nice fluids that don't have a quasi-particle description whatsoever. All the resonances are extremely broad. They don't have a quasi-particle spectrum. There's not even a peak somewhere in the spectral density that looks like a particle. So we're not sure, but there's a sort of a standard theory is to say that the quark gluon plasma actually does not have any quasi-particles at all. It's just a fluid. And that's one of the reasons that I sort of like this effective field theory description, because it doesn't make any notion of particles at any point in derivation, and yet you get fluid dynamics out of it.
Okay, and I completely agree with you, except that you can take the transport equations and put in things like effective self-energies and other things that would include at least some of the things
Yes,
that you're talking about.
but that's all recoupling quasi-particle approximations.
I mean,
That the whole spectral function doesn't have a peak. It's just not in there.
okay, anyway.
Yeah. Okay, so the question that sort of comes out from this is, okay, so it seems like hydrodynamic models actually are able to describe the data. The question that we haven't answered yet is, why do they do that? Why does hydrodynamics apply rather than maybe sort of a more straightforward model where you have different degrees of freedom, such as particle-like states that sort of interact with each other? Similar to that and sort of related to that is, okay, so usually sort of hydrodynamics makes this notion about equilibrium that was pointed out before. So if we think about the system being actually thermal, can we then understand the equilibration mechanism and also the equilibration timescale, which remember has to be short compared to the lifetime of the system, because otherwise there's no way that we can actually sort of describe or actually at least explain why hydrodynamics does such a good job as it does in describing the experimental data. So there are sort of mysteries out there. The way that I'd like to take is I'd like to sort of focus on the second question and think about what we can say about far from equilibrium equilibration, meaning you take a system and you don't just sort of perturb it slightly and see its relaxation back to equilibrium. No, you take a system and you basically just blow it apart, you collide it with something else. You sort of create a very far from equilibrium initial state, and you'd like to study how that system comes to thermal equilibrium, if it does at all. And we'd like to sort of have a model system, in particular for these heavy ion collisions. So the idea would be that okay, if we could sort of have such a model system, we could study how hydrodynamics starts to apply and how sort of this sort of natural description of the experimental data could be explained. And really sort of the only model that I'll sort of talk about is this gauge gravity duality, which sort of may provide such a model that has at least some bearings on the heavy ion collision experiments as we sort of see them. So I'm not really sure. Maybe most of the people in the audience are experts on gauge gravity duality, but I sort of included a few sort of motivation slides nevertheless. I hope that's all right. So what does the conjectured ADS-CFT relation actually say? In my words, basically what it means is that there is a conjectured duality between conformal field theory, conformal quantum field theory, in, let's be simple, 3 + 1 dimensions for a large number of colors. So it's a non-abelian gauge theory where n is the number of colors, and large coupling. And the statement is that that theory is dual to classical gravity in a space-time that's one dimension enhanced, in this case 4 + 1 dimensional, and is an asymptotically anti-de Sitter space. It's a space with a boundary in 1 dimension. And this sort of duality makes specific statements about how you relate quantities in one quantum theory in 3 + 1 dimensional space-time to the other classical gravity in 4 + 1 dimensional space-time. Okay? And I'll sort of give a few examples of these. The idea would be that you use sort of this tool to study a particular quantum field theory. In this case, I'll be talking about n = 4 super-Yang-Mills, which is sort of the best studied example of such a duality, by solving classical general relativity equations in anti-de Sitter space. So here's some entries of the ADS-CFT dictionary. The sort of thermal state in the quantum field theory side actually sort of corresponds to a black hole, or rather more a black brain, in this 4 + 1 dimensional space-time. And the idea would be that the temperature of that thermal state in field theory is dual to the temperature of the Hawking radiation of that black hole. So that's one entry in this dictionary. Another one is that the metric of the space-time that you're actually studying, if you sort of say you want to have just Minkowski space, that metric is dual to the metric on the boundary of this asymptotic ADS space-time in 1 dimension. So this anti-de Sitter space has a boundary, and that boundary is 3 + 1 dimensional. because it's the boundary of a 4 plus 1 dimensional spacetime. And that metric is dual to the metric of the field theory that you actually study. So if it's Minkowski space in one case, it's Minkowski space in the other. If you're interested in studying quantum field theory in curved spacetime, you can do that by writing down the explicit metric on the boundary of this higher dimensional space. The key quantity that I will be interested in are operators of this quantum field theory, such as in particular the energy momentum tensor. You can also think about others. Those actually turn out to be near boundary expansions, or given by near boundary expansions of the line element of these 4 plus 1 dimensional spacetime. And I'll be more explicit about what I mean by that, but I have to choose a gauge to actually show you what I mean by this, because it's easier this way. The full quantum dynamics of the field theory on 3 plus 1 dimensional spacetime is dual to the classical dynamics in this spacetime that has one more dimension. And that might come as a sort of biggest surprise in this whole dictionary, given that how can classical dynamics ever sort of capture quantum dynamics in any approximation, right? It's a little bit less mysterious, maybe, if you think about what has happened in sort of the development of quantum field theory that has to do with, for instance, stochastic quantization, where essentially you take a quantum field theory, you add another time dimension to the whole setup, and by doing so, you can actually prove that sort of random motion in this extra time dimension, classical random motion in this extra time dimensions can be used to just completely recast the quantum quantization procedure in the usual formulation. So in some sense, there's this notion that if you add one more space dimension or one more dimension to your space-time, you can capture quantum effects is not completely new. It's just sort of another example in these ADS-CFT dualities.
Can you give some concrete examples?
Yes, I will. Yeah, I will. Yeah. So, okay. So, in some sense, the issue we are facing is that not many of these duals are actually known explicitly. The sort of best known example, as I said, is n equals 4 supergamills, which actually is dual to supergravity approximation of type 2 string theory. In this case, it's sort of an ADS5 space with an S5 at every point in space-time. And in this simple case, the S5 doesn't actually play a role. So at every point in space-time, you would have an S5, which in principle also would have degrees of freedom. But in this sort of particular sort of duality, we don't care about that. We just sort of fact out the S5. All we have left is this 4 plus 1 dimensional space-time that is asymptotically ADS. There are some actual checks on this duality, meaning that people have calculated the same observable in the quantum field theory and using this prescription in classical GR on the space-time, and the answers match. Okay, so there are some actual checks on this. There are some other duals that I'll actually be not talking about, where, for instance, you break conformal symmetry. But yeah, so the best studied example is this one, and this is what I'll be using mostly. In particular, a dual to QCD is actually not known. People sort of try to make duals that are sort of more similar to QCD, but nobody actually knows how to write down a gravity dual to QCD, which is bad because then we could really sort of do very interesting stuff. We could sort of look at the ground state of nuclear matter, figure out whether there's a quark condensate in neutron stars or not, all these nice things. But unfortunately, that's not, nobody sort of knows how to do that right now. So we basically do the next best. We sort of use a theory that we can write a dual for. And the idea is that if you sort of think about the problem of these heavy ion collisions, the dynamic QCD problem is actually not solvable. And one of the reasons is this sort of called sign problem that prevents you to actually sort of put the problem on a computer, lattice QCD. Also because the coupling is strong, you can't really do perturbation theory, basically outside the bound of applicability. It's a many-body system, so you can't do single scattering as in high-energy physics. So really, there's not a lot of tools that you have to treat the problem in QCD. So the idea that I'll be advocating here is, rather than trying to solve the problem for QCD, you look at a different theory, in this case n equals 4 supergamills. You sort of send the number of colors and the coupling constant to infinity, and you sort of try to figure out what the answer is for that problem, and then see whether you can learn something from this. Okay, so if you do that, if you buy this, then we can actually use gauge gravity duality to study the problem. However, we have lost some problems or some features of QCD along the way, which is asymptotic freedom, confinement, and we typically have many more degrees of freedom than quantum chromodynamics has. So we are sort of treating a completely different system, which has some properties with respect to that are the same with respect to the problem that we can solve, but it's a different theory. So we want QCD with 3 colors and coupling of the order of 1, and we can do n equals super Young Mills with an infinite number of colors, infinite coupling via gauge gravity duality. So essentially, what we propose to do is we want to use theory. I don't know what that means. We want to sort of calculate a theory that's not realized in nature, that has the wrong gauge group, has the wrong coupling value, and is only conjectured to be calculable with the method that we're actually using. So you might ask, why the heck do we do that? The reason really is that we are desperate. We don't really have any other tool. Lattice QCD doesn't work for real time. Classical chromodynamics does not equilibrate. Classical chromodynamics plus scatterings does not equilibrate. You get all the results you get are inconsistent with experiment. Really, ADS50 is the only model that we have, and that's why we use it.
But the absence of confinement, I mean,
yes.
You're dealing with a system which confinement is broken down, essentially.
In our system, there's no confinement. It's conformal. It doesn't have confinement.
No, I understand, but the physical system...
The physical system, of course, has confinement.
But it's broken down in quark gluon.
Indeed, yes. And you may argue that actually the loss of confinement is probably one of the lesser worries that we have, because we're sort of looking at energy scales where confinement doesn't really play a big role anyways. So it's true that some of these issues may actually not be as bad as a sort of highlighted here.
The other issue is formal gradients versus supersymmetry. So
supersymmetry is actually broken at finite temperature. So it's actually not supersymmetric anymore. Yeah. So supersymmetry is broken, yes. Yeah, before you do anything, if you go to finite temperature, supersymmetry is broken. But you still have more degrees of freedom, you have more number of colors, and you still live at a coupling constant that is much larger than the value you think you should be simulating at. But yeah, so I can talk about all of these issues in more detail. But it's a drastic approximation, but some of the approximations may not be as bad as they sort of look at first sight, basically. Anyways, let me continue my story. This is a slide where I sort of tried to spell out a little bit of the details of how this actually works. So one of the things that I will try to write down is I will try to write down the first of all, the line element of a single nucleus moving at the speed of light. That's my first ingredient because I want to study collisions of these systems. The first thing I have to write down is the energy momentum tensor that corresponds to a boosted nucleus, a nucleus that's moving fast with respect to me sitting in the lab frame. And there's ways to do that. One of them basically sort of tells you that, okay, if you go into particular coordinates, then the relevant entry to the energy momentum tensor, the plus component, is basically given by a density. So the plus component is basically the direction of the nucleus traveling. And then you have a density, for instance, a charge density, that's dependent on the direction transverse to that direction. So the x-perp is the coordinates transverse to that beamline. And then because you boosted the system to very high energies, because of a Lorentz contraction already, you have a delta function that restricts the nucleus to sit at only one particular value in this time-like coordinate, basically. So you can write this down. This is just the energy momentum tensor of a fast-moving charge. I think even Jackson may have in his textbook. And then the question is, okay, if you give me that, what does that look like in the dual theory? And there's a fairly straightforward prescription that tells you that, okay, I want to have a line element that's asymptotic ADS space. So I want you to look at this line element here and forget about this last entry, but look at everything else. Then this first part here is nothing else but empty ADS space in 5 dimensions. The first 2 coordinates are the x plus and x minus. These are my 2 light cone coordinates. These are the 2 transverse coordinates with respect to the beamline. And then I have a 5th coordinate z, which basically parameterizes the distance from the boundary. So the boundary is at z is 0. Remember, the spacetime has a boundary. And then as you go with z to larger values, you go into the bulk of the ADS spacetime. So without that term here, that first part here is a line element that's just an exact solution to the Einstein equations with the cosmological constant, negative cosmological constant in 5 dimensions. That's what it is. And then there's a prescription that tells me that if I want to sort of include a line, if I want to include an operator, in particular this energy momentum tensor, into the setup, I can do that by basically writing an additional entry in that line element that's corresponding to these components here. So the t++ will have a line element entry that has a dx plus squared. And the delta function here will be the same delta function as there. And then the remainder is a function that basically corresponds to this energy density rho times a z to the 4th term. So it's a near boundary. The boundary is at z is 0. It's a near boundary correction to that space-time line element that's asymptotic ADS. And yeah, so basically that there's one explicit construction of how you take an operator in a quantum field theory, in this case the energy momentum tensor, and translate it to a line element in the ADS space. And this line element here also is an exact solution to Einstein equations with a negative cosmological constant in 5 dimensions. Okay? So that's one way of how you explicitly construct one of these things. Already you can sort of infer that what I can, for instance, do is if I sort of modify that line element here and sort of have dynamics that, for instance, change this component here, that would correspond to a change of the energy momentum tensor in my quantum field theory. And this is the way that I'll afterwards read out information. Are there any questions on that? So I think that's maybe one or two of two explicit slides that I have for the constructions. But anyways, so if you do that, then you can also write down what happens to an initial state that corresponds to 2 of these moving charges in the spacetime. They just correspond to 2 of these, superimposing 2 of these line elements together in the ADS space. And if you look at that, then you find that actually looks very much like these Eichelburg-Sechsel shock waves that were studied in the 70s in GR, basically. This is what it looks like, because you have these plane gravitational waves from the holographic or GR perspective. So basically, this simple model corresponds to the analog of black hole collision or shockwave collisions in a space that's ADS5, basically.
So in what sense exactly is it a shock wave?
It's a shockwave in the sense that you have a delta function here, so there's a discontinuity there. Yeah. So these are exactly the same ones that for instance, yeah. I mean, there's a lot of literature on the shock waves.
But is the interpretation that it actually is gravity wave transform?
Yeah, in this case, it actually is a gravity wave.
Speed of light gravity.
Yeah, that's right. Yeah.
So
Yes.
that speed of light thing is the shock.
Yeah. Yes, the shock is moving at the speed of light. That's right. Mm-hmm.
Okay, and so that's the shock.
That's my shock wave. Yeah, that's right. So in this simple model,
So it's not a shock in, I would refer to a shock in other ways as well, not just something with a boundary like that, but something that has randomness on one side and uniformity on the other, so like Mach's number. Yeah. And that's not what this is describing.
so this has there is no change in the entropy going from forward to backward. There is just a discontinuity, the entropy at that particular point where this shock wave is
Well, the
moving.
way one thinks of that, I mean, I know this is being described by an equation of state, but the way you think of that is that you have all of this motion which is occurring in turning something with, I mean, if you think about it in a shock frame, but here you can't because of the speed of light.
Right.
You think of stuff that's moving through the shock front, and it becomes it becomes random in its flow. And here, it's not meant that way. It's essentially meant as a discontinuity.
Right.
And that's all.
Yes, that's all. And there's nothing moving here. So in this case, there's just this one shock. There's nothing moving through the shock. Here, there's just one shock.
Gentlemen, do you actually refer to this as a shock?
Yeah, it's the proper term is a shock wave. You derive it either, you can construct all kinds of exact planetary solutions. The GR, they can have any profile you want. They'll solve Einstein's equation exactly. This one you can get out of the limit of taking a black hole, boosting it to infinite gamma factor while simultaneously scaling its mass down. And you call it a shock wave in a more formal sense, I think, of fluids where you don't worry about the internal structure of the fluid. It's just that you can have these singularities in the quantities you're interested in, like the velocity field, or in this case the metric, which then propagate according to certain rules. And those singularities you call shock waves.
Are these like Israel junction conditions? And I don't see why they would go.
There is something like the Israel junction condition that will come eventually once I collide two of those. Yes. Not if you have just a single one. There's nothing there. Yeah.
Nothing happens if you have just one shock wave, then that's the whole universe.
Yes.
It's just there. There's nothing else. So you have to let it hit something.
Yeah, but there's inside and outside.
There is no inside and outside. It's just a shock. Yeah. Okay, good. So the issue is that, okay, I would like to sort of actually study the collision of these two shocks, gravitational waves, basically. Obviously, that problem that I've set up would be extremely hard to treat numerically, simply because you have these very strong discontinuities. That's really a problem that my numerical GR friends say, okay, this is not really doable. You can't really collide shocks on shocks numerically, especially not in 5 dimensions. But so the main point that I sort of brought this up is that essentially some of the, at least some limited insight actually can be gained by sort of actually doing the shock-shock collision problem analytically. There are some quantities that you actually can calculate within there's some caveats with this, but some of that actually may be done. And basically what I'll sort of talk about is that actually that's what we did. We sort of calculated the profile of the energy momentum tensor after the collision of these two shocks, and then used it as an input to the hydrodynamic model that I was referring to in the beginning of the talk. So we basically used this to get initial conditions for hydrodynamics from these ADS CFT gravity. And this is a plot that's coming out from the simulation now again in the boundary theory. So there's no gravity here, it's just boundary. And basically what you have is you have the, so time starts here, and that's the radius of the whole system. And essentially what you find is that the temperature here sort of heats up first and then sort of drops again. And you can see sort of the flow profile, so the fluid velocity locally. So here it's higher than over there. But the main point that I sort of wanted to sort of get to, and I sort of took a very circuitous route and long time to get there, is sort of this region here. It's sort of white in here. And that's a region where we actually cannot define the fluid velocity. This actually is the main topic of my talk. So basically, what I mean by that is that if you want to define the local rest frame, then what you do is you look at your energy momentum tensor and you try to find time-like eigenvectors. That's the equation that you would solve in some metric, time-like eigenvector. This u mu would be the time-like eigenvector. The condition is in some metric that u squared is normalized to -1. And what I'm telling you is that there are these conditions here where that just doesn't work out. You don't find an eigenvector, time-like eigenvector of the energy momentum tensor. So there are many reactions to this. One of the reactions that I sort of want to sort of preempt is that some people sort of say, okay, well, and that's not surprising given that you're not in equilibrium, you're somehow out of equilibrium, so why should there be a fluid velocity? But the statement that I'm sort of pointing out here is stronger than that. It's stronger than that because I'm not even talking about a fluid velocity. I'm just talking about being able to transform to a frame where the matter is not moving. Okay? And I'm claiming that that cannot be done for this particular setup. I can actually go through the details of it, but I don't think I have actually that much time. I just want to say that if you think about kinetic theory, where the energy momentum tensor is given by the usual expression here, you can prove that that condition is, so that the condition meaning that you get local rest frame condition is always possible. You can always define the local rest frame for a gas of particles. You'll never sort of find this. Okay, so in classical kinetic theory, you never have the problem that you can't define a local rest frame. Also, in classical field theory, you can actually work through, and you find that also there you never have a problem. You can always define the local rest frame, no matter what you do. So this is why we say this is a quantum problem. And actually, before I go there, you can actually, let me sort of fast forward to, so you can actually sort of look at that example in more detail, but before I sort of wanted to sort of point out the following. So we sort of see this in numerical simulations of this n=4 super-Young theory. You might argue that, okay, maybe what we see is some sort of numerical artifact and that's actually not real. Another group has actually seen the same thing using completely different code, completely different setup, maybe having to do with super radiance of black holes, but they also sort of find the same phenomenon. But still, I mean, you could argue that, okay, this is a numerical code, so maybe the same problem somehow plagues this. I want to argue that we can actually show this analytically. And to do so, we basically use techniques that are actually fairly old. We basically sort of consider free massive scalar theory, quantum field theory, and we'll consider two particle state that we construct in a particular way, sort of the vacuum plus a small perturbation times this two particle state plus another perturbation times the vacuum state. And then we calculate the energy momentum tensor from this, and there's a way to do this. And if you do so, then you find that the local rest frame condition sort of takes a particular form here, and we have this one free constant alpha here that we sort of set up in our initial state of the field theory that we can choose. And if you choose it to be a particular value, you find that actually in this simple analytic model, you can violate the rest frame condition. Okay? So the point here is that we can show analytically that a local rest frame cannot be defined in a simple quantum field theory. You just have to find the right state. There are some properties about this. So first of all, the absence of this local rest frame is usually confined to a certain patch of spacetime with an extent that's in some sense given or fixed by the uncertainty principle, so that if you average over an uncertainty region, you don't have any problems. But if you look at scales smaller than this, you do. The other thing that I wanted to mention is that, let me sort of go backward, is that actually this local rest frame condition, you can actually rephrase it in terms of energy conditions and GR. So one of the ways to do this would be you look at the weak energy condition, which just states that all time-like observers see non-negative energy density if a particular condition holds. Actually, that is the same condition that you find if you argue that there should be a time-like eigenvector to the energy momentum tensor. So these conditions sort of are related to each other. Yes?
I'm trying to reconcile, I mean, you're talking about the local rest frame condition.
Yeah.
I think I understand what that means, but to me the rest frame of a fluid would be something that could be defined globally by calculating the total momentum associated with your total system.
You can also define a global rest frame if the whole, I mean, basically what you're talking about is the global velocity, if you want to, of a blob of fluid. But that's actually a very, I mean, yeah, so that I mean, for that, in some sense, to be interesting, the whole thing should actually move with one common velocity or something like that. What I'm talking about is that at least locally, I should be able to sort of boost to a frame where the matter with respect to me is not moving. And that can be different at every point in space, that's fine, but at least I should be able to do that. That's a much weaker condition than having some global sort of flow velocity.
But I can still be comforted by the fact that there's a global rest frame for the entire system.
Yes. Yes. Yes, that's probably also the true for us. If you, in some sense, that's in some sense similar to what I said, that these regions where we can't define the local rest frame are usually they're sort of just some patch of spacetime. They're not arbitrarily large. And if you sort of take a sort of average, which you would do if you wanted to define a global rest frame of the whole thing, then usually that would work out. You would have not a problem with that. So it doesn't violate these averaged energy conditions, but it certainly does violate the weak energy condition and also the null energy condition in the examples we studied in flat spacetime. Okay, so there's no non-trivial spacetime. There's no funny quantum fields that we put in there. So in this case, it's really just free massive scalar theory. no exotic ingredients whatsoever. I didn't get as much covered as I wanted to, but maybe I want to go ahead and wrap up. So the local restroom condition actually is harder to violate than the energy conditions that we looked at. So typically, if you violate the local rest frame, then you violated everything else as well. If you violated just an energy condition, you can still have situations where the local rest frame can be defined. Okay. That's what I said. Typically, the energy conditions are only violated locally, and the patches are confined by, loosely speaking, uncertainty principle sizes. So that means that if you average over these larger patches, then the energy conditions should be satisfied. One of the interesting consequences of this is whether there are any observable consequences of that. The reason that I bring this up is that this flat space-time and all of our knowledge, I think that's fair to say, all of our knowledge of observables are based on the notion that we have a local rest frame. If now I tell you that there are regions where that cannot be defined, it's extremely hard to just repeat the calculation of pretty much any observable and say what is the difference there. Okay? Because usually you say, okay, you have a local temperature, the system is locally at rest with respect to something. I'm telling you that none of these things can be defined for these particular examples. So the question is, can you find properties of quantum matter without a rest frame that are first of all can be calculated, and whether any of those are actually different than the corresponding situation where you do have a rest frame. Maybe they are similar to the properties of quantum matter that does have a rest frame, maybe they are not. The nice thing about the ADS-CFT gauge gravity duality is that in principle it opens up the possibility to actually study these observables without their local rest frame. So in ADS-CFT you can study correlators purely from a quantum field theory perspective without ever recurring to the notion of a rest frame. So what I'm thinking about in particular is current correlators to define the photoproduction or something like that. That could be something that's calculable even in the case where you don't have a local rest frame. And then you can possibly look at those observables and look at it in comparison to regions that do have a rest frame. So basically what I want to say is that this is really uncharted territory in the sense that nobody has calculated what happens if you don't have a rest frame, whether that has strong or weak consequences for observables. And this is really something that people should be looking at. And we started to look at some of these things. But there's probably a large class of things that could be interesting. And since I guess I'm out of time, I'll just stop here.
Can you give another example of how classical dynamics and 4 plus 1 corresponds to quantum dynamics and 3 plus 1?
Okay.
Sounds fascinating.
Right. I don't think I have a slide for that, but basically, yes. So basically the idea is that it's similar. So there, you can try to set up something like a Keldysh formalism and the equivalent of a Keldysh formalism in the gravity. But basically it really boils down to you study real-time phenomena in one theory whose boundary is essentially given or defined as the quantum theory equivalent. And in that sense, very naively, basically these two things correspond to each other. So you have a quantum theory on the boundary, and that quantum theory really corresponds to a classical theory in one more dimension. That's really how it corresponds to. The example that I can say is what I alluded to a little earlier, is stochastic quantization, where you just add another time dimension, and you just have Brownian motion with respect to the other time dimension, and that acts as stochastic, in this case, quantization of the field theory. I'm not really sure if that helps a lot, but yeah.
So in the stochastic quantization, you have an ensemble average, and is that the analog of the quantum averages? So that's not exactly a boundary.
Right. Yes. So here basically the the expectation value really comes through. No, there's not really a stochastic average in this case. It's really sort of that the average, the expectation value is defined as a particular near boundary expansion of the line element.
That's in this case.
In this case.
Stochastic quantization.
Yeah, in this case, not in stochastic quantization. It's right in stochastic quantization. That's how you get the expectation value here. Yeah. But in this case, it's really sort of that the. So if I write my line element, I have basically AES space here. The simplest one would be a Z4 here. And then the part of the line element that corresponds to the next correction with a Z4 term is the expectation value of the energy momentum tensor. Higher orders, I don't know, maybe C6 or so would come in with 2-point functions and things like that. That's the way that sort of appears. But
People want to leave, we can
yes,
talk offline.
yeah.
Well,
Yeah,
We're cooking upstairs, so.
Right. Yeah, maybe let's move the discussion upstairs and let's.
Yes, sounds good.
Yeah.